So just to warn you, Audric will get interrupted, hopefully get interrupted by a student who needs to take a test in about 25 minutes or so, if we're lucky. Well, if I'm lucky, but we'll see what happens. But anyway, I will begin with a word of prayer. So, Dear Father, we thank you again for this opportunity we have just to meet together and study your creation. Just pray you to guide our thoughts, Lord, today. In your name I pray, Lord Jesus. Amen. So yeah, we were just starting to talk about convergence almost everywhere. And one of our immediate goals is to contrast the concept of convergence almost everywhere versus convergence in norm, right? So I wrote those two definitions up here to get us started. Convergence in norm, you start with a sequence of functions that are Lebesgue integrable, and you say that they converge to, that sequence converges to f in norm if the sequence of the absolute value, the sequence formed by integrating the difference of the functions and the limit functions, the absolute value of those integrated, actually that sequence converges to 0. In contrast, convergence almost everywhere, we start with a sequence of functions. Notice we're not even assuming that they're Lebesgue integrable, right? You start with a sequence of functions defined in R. They converge to f almost everywhere, denoted by fn converges to f AE, if fn of x converges to f of x for all x except a null set. So it's essentially convergence almost everywhere is sort of a slight weakening of pointwise convergence, right? Certainly, if a sequence of functions pointwise converges to f of x, then it converges almost everywhere. Yeah, because pointwise convergence is just like, you take the sequence of functions, you evaluate at the point, that gives you a sequence. If that sequence converges to the value of the limit function at the point, if that happens for every domain, every point in the domain, then that's pointwise convergence, as contrasted with, uniform convergence, which was, remember, so we talked briefly about pointwise convergence, which in some sense, from the viewpoint of this book, is not natural because it's not convergence in a norm. Like he proved earlier that there doesn't exist a norm which reproduces pointwise convergence as the convergence of a norm on function space. Which is a point which is not made in my other real analysis books. So I guess that's important to hear, but less important to real analysis. Certainly pointwise convergence plays a role in real analysis, just, regular, plain old garden variety. I'm mostly thinking of I like this book by Rosenlicht. It's a little Dover book. I think that's the spelling, it's just a little Dover book. It's a great introductory real analysis book. It's a nice place to review basic real analysis, and it's a nice little book. I sometimes look at that if I just need a refresher, But anyway, okay, so theorem. Let's do the theorem. I don't think we did this theorem yet. So let's do the theorem. This is theorem 2.77. It says that suppose Fn converges to f almost everywhere, then Fn converges to G almost everywhere. If and only if, I lost my bearings here. If and only if what? If and only if, well, what would you expect the conclusion here is if and only if what? F and G are equal, right? But then what? But almost everywhere, right? You say that's weird?
Yeah, because, they're equal. What do you mean functions aren't equal except on a specific set of points,
No, they're equal everywhere except for a set of points that measure 0, except for a null spot. Null set. Well, here's the proof. If Fn goes to F almost everywhere, all right, and Fn goes to G almost everywhere, then Fn minus Fn goes to F minus G almost everywhere, right? But of course, Fn minus Fn is equal to 0, right? So, which implies that F minus, F minus G is equal to 0 almost everywhere. So, and here I'm using the properties of the almost everywhere convergence, which are stated right above the theorem. So, we could, I suppose we could, let me think here for a second. I mean, what is it? What does it mean for 0 to go to F minus G almost everywhere exactly? Because that's what we have, right? This is the, this is the 0 sequence in that sense. Like, I could call it, let me call it H sub n, all right, goes to that almost everywhere, or Hn is equal to 0, all right, for all n. Well, the definition right above means that Hn of x, right, goes to f of x minus g of x almost everywhere, right? But this is 0. So and so the zeros, we know what the 0 sequence goes to. It goes to 0. So that immediately gives you this, right? Almost everywhere. Which then says f is equal to g. F of x is equal to g of x, almost everywhere. Hopefully I'm not abusing notation. He tends to only use almost everywhere at the level of functions. I'm also using the notation at the level of points. I'm not sure that that's, hopefully that's not problematic. I don't think it is.
It's almost everywhere for the function itself. It literally means this for a set of points where it's a null.
Right. Yeah. I guess there's the converse direction. Now assume that Fn goes to F almost everywhere and F is equal to G almost everywhere. And well, I guess I could write it down. So the converse direction. Sorry, Audric, I'm not myself today. It's so hot in this stupid 4th floor. I don't know. Maybe it's hot to me. It may be not hot to other people, but it's just warm enough outside that they don't have any air conditioning on. It's just unpleasant in here. What's that?
I'm just trying to put my understanding when I got in a row.
Okay. So now assume Fn goes to F almost everywhere and F is equal to G almost everywhere. We're trying to prove that Fn goes to G almost everywhere, right? That's our goal at this point. The converse direction of the proof. And he says, let A be, all let A include all x in the reals for which fn of x does not converge to f of x. And by B, the set include all x in the reals such that f of x is not equal to g of x. All right. He says, okay, so A and B are null sets. Right, that's by assumption, right? Because both of these are almost everywhere statements, right? So that means that the place where you don't have convergence and the place where you have non-coincidence, these are both null sets. And then his point is, okay, so the union of two null sets is null set. All right. And then he says, since fn of x goes to g of x, excuse me, for every x not an element of A union B, we find fn of x goes to g, rather fn, my bad, fn goes to g almost everywhere. All right, which is what we're trying to prove. Yeah, yeah.
Okay, this might be a dumb question.
Go for it.
So, he says Al assumes Fn goes to F almost everywhere, and F equals G almost everywhere. Like, doesn't he assume what we're trying to prove here?
No, because the if and only if is that fn goes to g almost everywhere. So the fn goes to f almost everywhere is a precondition of the statement.
Okay.
So we assume fn goes to f on both sides of the implication.
Okay.
Yeah, yeah. He really should have just said, suppose fn goes to f almost everywhere at the start of all this and said, forward direction, reverse direction. But he's including it here just because it's important for setting up the set A, right? And the context B, and then so A union B is a null set, and then since we have convergence on everything except for a null set, that gives us convergence almost everywhere by definition. So, all right, let me get to the example. Let me get to the, what's that?
The union of null sets is null.
Yes, the union of null sets is a null set. And you can prove that basically by, yeah.
And it's going to be 1, 2, and so therefore no.
I was thinking like a compartment where the measure set had to be something like a union of
Well, yeah, I mean, basically if you want to run through it at the level of null functions and thinking about building a step function whose integral is 0, and you have another step function whose integral is 0, then you could build a step function for both, for the combined union of the sets, and that step function would still have an integral which is 0. But I mean, it depends on how you're coming at this, how you'd prove that, Okay, so this is the example I was a little bit excited about. Here we go. I like examples, especially for this kind of material. Examples are oftentimes very enlightening, right? In terms of understanding definitions, especially understanding the difference between definitions. Examples are so helpful. 1, 2, I always get annoyed when I have like a really beautiful book with no examples. It's like, just come down from the clouds for a second. Give me an example. There are books that just don't have examples and yet are really good books. Those are annoying. Anyway, 1 over square root of n. And the reason for that usually is that the examples would make it not beautiful if you were to include them, That's the why. So 1 over the square root of n for x and minus n to n, and 0 otherwise. All right, so it might be helpful to just graph a few of these, yeah? Before we do anything more. Let's just try to understand what we're looking at here. What's this thing look like for, let's see here, for like n equals to 1. We're like 1 over the square root of 1, right? So it would just be like this, right? Here's f1. And then what's f2 look like? f2 goes from minus 2 to 2, but it's 1 over the square root of 2, right? So it's like that, right? Yeah?
This be complex too, if x is in the closer from negative to n, it's going to be less.
Oh no, this is all real. Here n is.
Oh, sorry.
Yeah. I got you, but no, it's. So and then what's 1 over square root of 3? I don't know what it is, but it's smaller than 1 over the square root of 2, right? And it's so, and then that one stretches from there to there, right? So here I'm drawing, the graph, if you will, f1, f2, f3, and you see the situation gets worse. Well, I mean, does it get worse? I don't know. Notice that while these are not step functions, technically, I mean, well, no, they are. These are step functions, right? It's a characteristic function times a weight, right? So, I mean, I think you could see these as step functions, I believe. Okay. Let me erase that over there. Turn the page. What's his? Okay, so we have some sense of what we're looking at, yeah? I think that these are Lebesgue integrable. I want to say. Where did my, oh man, oh, over here, duh. Okay, so observe, oh man. Oh. All right, so things we can see. Fn of x goes to 0, for x going to infinity, for n going to infinity, right? And that's true for all x, right? We have that, right? And like I was saying, so in other words, this is just what I was talking about. In fact, this sequence of functions pointwise converges to the 0 function everywhere, right? There's no even, there's really, I mean, he says almost everywhere, right? So he's like, okay, so Fn goes to 0 almost everywhere, and you'd be like, almost everywhere? It's just everywhere. But everywhere implies almost everywhere, so. It's just that your null set is the empty set, so hooray. What's that, Audric? It's all just a word game. So, all right, so this converges to 0 almost everywhere, right? But on the other hand, what is the integral? On the other hand, what's the integral of the absolute value of Fn? So think about it this way. You've got, I mean, you can just fall back on basic ideas because all of these things are modeled over basic length times width is area, right? That's at the base of everything. So if you sort through it, the height is 1 over the square root of n, right? The width is 2n. What's the area? Yep, 2 square root of n, because n over root n is just root n, right? So this is this is 2 times the square root of n, which of course goes to infinity as n goes to infinity, right? Which is to say this sequence of function converges to 0 almost everywhere, right? But it diverges in norm. It does not converge in norm. See, because convergence in norm, remember, is this. And so let's see here. Yeah. So yeah, at least at the very least we could say it doesn't converge to 0. Okay.
But I thought convergence with norm was already like a thing we explained as like not the same as divergence. So
Well, we're still explaining that. But I agree with you. There's something missing a little bit in that all this shows for sure is that it doesn't converge to 0 in norm. How do we know it doesn't converge to something else in norm? I think there was a theorem which linked convergence in norm to convergence almost everywhere, maybe. Suppose Fn goes to F in norm. Theorem 2.75. Theorem 2.75 says, suppose Fn goes to F in norm, then Fn goes to G in norm, if and only if F equals to G almost everywhere. I guess that doesn't help directly. I don't know. I'm content to say that at the minimum, this example shows that it doesn't converge to the same thing, at least. In fact, worse than that, it diverges. That's pretty far removed. So example 2.79. Granted, there's something more to think about there. I agree with you. Consider sequence Fn defined as follows. So this time, Fn of x is equal to 1 if 2 to the k minus 1 is less than or equal to n is less than 2 to the power k, and x is an element of, golly, this is a lot, n over 2 to the k minus 1, comma, n plus 1 over 2 to the k minus 1, minus 1, and it's 0 else. He has pictures of these on page 57, which I will reproduce on the board shortly. All right, so let's see here. Let's look at n equals to 1. What's that? N equals to 1. You have, let's see here, 2 to the 0, which is what? 1. And 2 to the 1, which is 2, right? And so you're going 1 to 2, 1, you're going your value 1, right? From 1 to 2. Wait a minute. No, that's not. Wait. Oh, Oh man, wait, hold on a second. I gotta think about this more. Oh.
This kid just said
Yeah, so okay. Let me think about this some more. Which n? Oh, you gotta figure out which k, right? I should put really above here, there exists k and n, right? Is the more full statement here. That's part of that. So what k would put, if n equals 1, what k is between? How can I get 2 to the k minus 1 less than or equal to 1?
right? If k is 1, 2 is 0.
One. Yeah, that'd be one. K equal to one.
K equal to 1?
Yeah, because if n equals 1, k equal to 1, you get 2 to the power 0 is 1, so that's less than or equal to 1.
Yeah, and 2 to the k is 2.
To the power 1, which is greater than 2.
Okay, so it forces k to be 1, right?
Yeah.
And, oh hey, I'll be right back, you guys. Let me get my keys. I'll be right back. Let me move my mic here. Before I inadvertently get personal information on it here. We'll go this way.
Oh, and then x would have to be in the closed interval from 0 to 1.
For n equal to 1, k equal to 1?
For k, but yeah.
Yeah, k equal to 1. No. K equal to 1 will be,
Because you have 1 over 1 minus 1, which is 0. And then 2 over 1.
yes.
Yeah.
0 minus 1. Oh, yeah. I got it.
Oh, and that's the, does that correspond to the first picture he has in the book there, or I haven't looked at it yet. Or is that something different? What was that?
It says, oh, okay, figure 2.2. Yeah, that sounds right.
Okay.
Yeah, because I was thinking about 3, and I was just like, 3 should be similar to 2.
Oh, for n equals 2 and n equals 3?
Well, if n equals 3, k still has to equal 2. You can't equal 3.
Yeah.
So you get the same boundary conditions. No. You get oh, I see why, because the boundary, I'm sorry, the set which x comes from, that's to change to the positive come after the 1. Yep.
When n changes to 2 or 3?
N equal to 3, k equal to 2, which the set that x.
Yeah.
And okay, yeah, I get it now. Yeah.
Oh, I see, yeah, 1/2 to, yeah, okay, see.
Yeah, and then you kind of keep playing that game.
Yeah, huh,
And yeah, that picture actually shows kind of game going.
Yeah.
You're bouncing back and forth between airborne.
that's interesting.
Yeah. And it's actually making kind of like a ladder diagram, or a staircase diagram.
Yeah, huh.
So is the reason we care about the convergence and the norm and like is it because we typically just have both? Like if you have a sequence, the integral automatically, like you can't have convergence in a limit and convergence in a norm. Like I thought these were already separate notions of convergence, but I might be wrong.
Yeah, you mean convergence almost everywhere versus convergence in the norm?
Yeah, like I thought these were already separate things, but
Yeah,
I don't know.
I guess they
We
are.
talked about it one at the beginning and I just missed it.
Yeah, no, I mean, they are, I mean, there's the two definitions up there are definitely different, but I don't,
Yeah.
I just, like you, I'm still trying to figure out exactly where we're trying to.
All right,
Yeah, because
I'm back.
but we also have convergence, uniform convergence, otherwise convergence. Well, yeah. No,
Yeah, point-wise convergence can't be in the norm, right? Because
Yep.
Oh, I think I see what you're posting now. That's interesting.
So we figured out that the only k that works for that, for n equals to 1, is k equals to
One.
1.
Yeah.
And that gets us from 0 to 1.
So that's that. How about n equals to 2?
Well, that gets us from 0 to 1 in the domain.
Okay, so n equals to 2 puts you k equal to what? Oh, I'm sorry. Yeah, what is it? Oh, my bad. N equals to 1 puts, so puts, so that makes this what?
0 to 1.
0 to 1.
It is 1, k is 1, so.
So it puts it 0 to 1 actually. So I lost track of where I was. So it puts it there, right?
Yeah. Which he also has in the book.
And then n equals to 2, what k works? 2, k equals to 2.
Yeah. Oh, yeah.
And then that makes x an element of what?
0 to 1 half.
Is that right?
Is right.
Yeah. 0.
What?
No, yeah, he's right, yeah.
Did you get it? Right.
Yeah, he's right.
Okay. Sorry, I was processing here. So that's 3 over.
The right endpoint is 3 over 2 minus 1, which is
So this gives you 3 over 2
yeah, minus 1.
minus 1. Oh, which is a half. Okay. So that's like this. All right. And then what happens?
N equals to 2.
N equals 3.
Oh, yeah, N equals 3. You still have K equals 2. This time you switch over your bound to 1 half to 1.
So x is an element of 1 half the 1, you say?
Yep.
So that would be like here. Funky. It's really weird, isn't it?
No, yeah, it actually just plays this game of like you're moving left or right.
Yeah, and so it does that. So I guess we got to the one, two, three. I guess the next thing it does is it shifts back over here like a quarter step, right? And then it goes like a quarter step over, and then it goes like a quarter step over, then it goes like a quarter step over, something like that. And then it goes to eighth steps. So you see what it's doing? Like whole step, and then half steps to one, and then quarter steps to, it's always, this is, my picture's not right. My picture's not right. It's